Yes, we are live now. Dipakshi ma'am, you can start.
Good afternoon, everyone. Welcome to the day 2, session 2 of Recent Trends in Domination and Graph Labeling, ADMA workshop. For this session, we have Chair Dr. A. Muthuswamy. He's a professor at Perrier University, Department of Mathematics. He has more than 20 years of research experience. He has awarded PhD to 5 students and 6 students are registered under him. He also has awarded MPhil to 22 students with 5 registered students under him. He has more than 50 publications in international journals. He is a member of Ramanujan Mathematical Society, life member of Indian Society of Technical Education, member of the Institute of Combinatorics and its application, and life member of the Academy of Discrete Mathematics and Application. Sir, we are lucky to have you. Please take over.
Okay. Good afternoon to one and all at the outside.
Afternoon.
Am I audible?
Yes.
Yes, sir.
Yes, sir.
Yes, okay. And first of all, I thank the organizers for giving me the opportunity to share the session. And I thank the organization of the Ramanujan College, the president or secretary and the administrative, the authorities, the principal and the organizing secretaries of the college for organizing such a nice workshop even at the pandemic situation. So with these few words, I would like to introduce the afternoon session's speaker, Professor Varghese. Professor Varghese had his master degree from Madras University in the year 2001 and his doctoral degree from MS Manonmaniam Sundarnar University, Tirunelveli in the year 2010. To his credit, he has published more than 70 research papers in the internationally reputed journals, and he has guided more than 15 MPhil and PhD scholars as an active researcher. He has operated one research project also. And recently, in the year 2018, he has been awarded a First Paper Presentation Award by the Science Society. So he's a very good researcher in the field of graph theory, and his specialized area is labeling of graphs. And in the today's talk, he is going to talk about different variants of magic labelings, especially the super magic and anti-magic labelings of graphs. So with these few words, I invite Professor Varghese to deliver his lecture on these different variants of labeling of graphs for about 45 minutes. I invite the Professor Varghese to deliver his lecture.
Thank you, Professor Muthuswamy. It's fine to come back again for this session. Hope you had a fruitful 2 days. Yesterday, the first talk, Professor Aramugam introduced to distance magic labeling and also the anti-magicness of certain graphs. I had actually taken you through some background of this magic labeling itself, of coming from magic polygons, and some of the tricks and strategies for reaching these particular magic graphs. Today, my intention is to take you through 3 important concepts: magic graphs, super magic graphs, as well as anti-magic graphs through these labeling techniques. I would go with this particular notion. Yesterday also I have mentioned this. This is not a difficult area of research. Persons with the basic sense of numbers and little sense of partitioning of integers, especially positive integer partitioning, we would be able to start this work. Of course, an idea of or an intuitive sense of recognizing patterns is going to be very advantageous for this kind of labeling techniques. a sense of optimization. Especially you might have, or you might have studied about knapsack problems, or even any other OR techniques would give it to, with the minimum condition, we have to maximize the output. So given a packet, how to insert as many as possible depending on our requirement. The knapsack problem concept would be used here as an optimization technique. And it's a funny area. It's real fun if you start with. Even if you're working in any other area of graph theory, combinatorics, mathematics, or even non-mathematics. There are some non-mathematics people also here, or even after your retirement, or even beginning of the PhD. I would even suggest many of us can take this to undergraduate students, so that they, with the very sense of numbers, the intuitive techniques, or sometimes innovative techniques that they use, they can come with a very good labeling, especially this magic, anti-magic, as well as super magic labeling. We go with the basic definition of magic labeling. As yesterday it was hinted to you, we have an injective labeling of the edges with the positive integers. From there, we induce a labeling of the vertices by summing up all the edge values incident to a particular vertex. And in case this particular sum is independent of the vertex we choose, it comes out as a constant, then we say this particular labeling is a magic labeling, and we arrived at a magic constant. Hope the definition is clear. I just put it in a very formal way here, but the simpler, draw any graph, label the edges with the positive integers. Being injective insists that we cannot label two edges with the same label. Now go to each vertex and identify all the incident edges to that, sum all the labels. Keep writing that. Initially, randomly, when you do that, we will get all sometimes distinct ones. Can you think about reworking on it and bring out as a single value? We begin with being a workshop, we begin with the smallest graph. Let's go with the K2. Can I just find out labeling for that? You can use the chat box to give me the label. It's quick. K2. Let me check that. What's the labeling you can give to K2 or P2? Just a single edge. Yes, you give the edge label 1. There is no issue with injection here, just 1. And vertices you are going to get 1 and 1. That's all. Only one edge is incident to both the vertices there. So 1 and 1. You can give 2 also there. Then but vertices will get the values 2. So it's very trivial and it is available. Now why don't you try with the next immediate connected graph? P3. Can you try with P3? Can you give P3 with an injective labeling of the vertices? P3. Actually, we need to have edges distinctly. We start from 1 or 2, 2 or 3, or 2 or 4. Now you find definitely a troubling situation. What's that you find there? Can you have a common a constant value for the vertices?
No, that cannot.
It is impossible. And this is going to be a pendant vertex is going to trouble us. Now you extend to any graph with a pendant vertex, just a single pendant vertex. Will magic labeling work? Because the moment you give that edge a value, that vertex is getting that same value. What about the other vertex? It has to go for a little more than that. Let's say x is the value for the edge. Pendant vertex will get the value x. But what about the other vertex? It would get x plus something. Therefore, one result immediately you got. That if in case a connected graph is having a pendant vertex, we cannot go for magic labeling. This, as per this definition, we cannot go for magic labeling. In case if you remove this condition of injectiveness, of course, we can work on maybe, and then it is not, may not be possible. So the problem is in the early stages itself, very moment existence of a pendant vertex, pendant edge is going to trouble us. It's not just one anymore, not even a single pendant edge, except the first graph, that K2 or P2. Other than that, we will not be able to find at all magic labeling. That's a warning sign, so you have to be approaching it carefully. How to go about the larger graphs? Magic square is going to help us identify a class of graph that is going to have. Yesterday I had shown you that. Look at this. This one is a magic square of order 3. What's the sum of each row and column? It's not a pan-diagonal magic square. It's 15. All of us know it's a very familiar and famous one. And this gives you a beautiful magic graph. Yesterday we had seen that, and this is the labeling that is available for that. K33 immediately we get. Many of you are familiar with the idea of creating this magic score of order 3. Yesterday I had shown you the method of creating a magic square of order 4. Now, any magic square of order 5 can be done in a very interesting manner. Some of you are familiar with that. And just for the people who are new to this, I'm just going to show you that. Yes. Yeah, you could notice this one. Let's say go on with the 5 by 5 or the order 5. So we start with the central cell on the top row. So general 2 or 3 small principles are, most of us are familiar with, in school level might have studied it. We go with the largest positive directed L in it. And continue to do that anytime when we reach a bottleneck, either we go diagonally or we just go to the immediate bottom lower cell and then you go diagonally. So keep always this largest L. So for example, one is the starting one. Then you go with the first L is this. Then no more positive direct L is possible because it has to go up and down. So what we do is we go to 3. Then from there is an L available. Sorry for this drawing here. Yeah, L4. Then we go with the 4, 5. We reach a dead end there. So we come down 6, then 7, 8. Then you come back, it's 9. So we go with another L here, 10. It was blocked by 6 there. We go down 10, 12, 13, 14, 15. Come down. We went for another L, 17. Then comes another L, 18, 19, 20, 20, 20. It was blocked by 16, so therefore 21, 22. Then again 23, 24. Last is L, 25. So this is, it can be extended actually. And giving us the sum, magic sum of, how much is this row sum or column sum? You can try on your own how it's 5 by 5 cell. It's for order cells. Easy formula we can find out. Yeah, that's perfect. We have, you remember Gauss way of addition. 25 plus 1, 26, 19 plus 17, 26, then half of that. 2, 26 and 1, 13. Yes, you go with the 5 if you, 7 if you want. Just same trick only we need to apply. 1, L is come here, then we go for 3, 4, then again is 5, then 6, 7, again 8, 9, 10, 11, 12, 13, 14, then 15, 16, 17, 18, 19. L is come here 20, then 21 here, L, bottom because it's blocked by 15. So in there diagonal is reached 28, then 29, 30, 31. So this method you can repeat for every odd order ones. This gives you a family of actually magic squares. In fact, one of the earliest results associated magic graphs was associated with the help of this particular labeling. Sorry for that. Yeah. If you do not insist F to be injective, that edge labels, then we get a variety of magic labeling known as semi-magic labeling. We can start with any of the values. We can give every edge one value. We get that is the most ordinary one that we are getting. Every edge one value. Therefore, magic labeling, semi-magic labeling exists for most of the graphs. In case we are not insisting on natural numbers, it exists for trees also. Pendant vertex, give 0 to every edge. You'll get every vertex 0. Therefore, we are not looking at those graphs where in which everything is 0 or everything is a constant, a single value. Especially in regular graphs, it is easier. But this gives you some idea from the earlier identification itself. Not all graphs are magic. Although the idea was brought out only in 1963, without much delay, people have come with the characterization of magic graphs. There are 3 distinct characterizations, partly as well as fully. Jorisan in 1988 and later in 1988 with extensive version of the characterization. Derrington Hunton in 1983. Jensen and Trengler, this is the most famous one. Jensen, easiest one also compared to all those. Connected to this, there is a beautiful algorithm for finding. Of course, that would not give you the optimal labeling, but you get always a magic labeling using this one. If the graph is magic, there would be getting. So all the graphs are not magic. Identifying whether a graph is magic is by the characterization. If you get time, please go through this, especially the last one. Through it is the fundamentally through factorization, finding 1-2 factors. Finding the graph of 1-2 factors, that is decomposing a graph. Yesterday, Professor Sedumadhavan is going to teach you on labeling and decomposition. So this is a method of decomposing or identifying factors. One factor, that is all the edges, individual edges, and then 2 factors, that is cycles. So if we can decompose a graph into C2s and P2s, sorry, not C2s, CNs and P2s, then this particular characterization is going to be very useful. So please, those who are interested in continuing with this work, please, I've just shown you all the details regarding that. These 4 works are very substantial and very milestone works on magic labelings. So characterizations are over, but that is not giving a full stop to it. Although some people have come with not all of them are very easy. Therefore, you can think about going for a better characterization or easier characterizations if available. So one of the major works we can do while continuing with this work is there any way of characterizing magic graphs, as well as different types of semi-magic graphs? Now, some non-results. Apart from characterization, which are the graphs that are already known to be, I'm not showing everything, but I'm going to give you a simple glance of that. The first one, we know, we already done, n is equal to 2 is possible, but C3 is not, K3 is not possible, K4 it is not possible, but K5 onwards, it is available. N greater than or equal to 5. Any complete graph is magic. KNN is magic for all n greater than or equal to 3. Complete bipartite graph, wherein which both the partate sets have a balance. It is also known as balanced bipartite graph. Both the partate sets have the same cardinality. We just work out for odd numbers, and even numbers also we can work out similar way. Fan graphs. Most of your, you take a wheel graph already, then remove one vertex from the peripheral vertices. What you get is a fan graph, fan in the hand fans actually. So fan graphs are magic if and only if n is odd and n is greater than or equal to 3. Something like this. The idea that I was mentioning was from wheel graphs. So we make it, you remove one edge or you just remove one vertex, then you will get a fan graph. From wheel you can develop. Fan graphs comes as a subgraph. Then we have the wheel graph, Wn, when n is greater than or equal to 4 is a magic graph. One more subgraph of wheel graph is magic. Wn with one spoke deleted is magic. N is equal to 4 and n greater than or equal to 6. This is one research direction. Although characterizations are available, can you find graphs that are subgraphs which are also magic? Can you find graphs, super graphs brought out, constructed from already existing graphs, magic graphs as magic? From KNN, how many more edges can be added so that it still remains as a magic graph? What is the optimal situation where which you can stop adding any more edges? Retain the number of vertices there. Two parallel, two divergent research directions you can have. There is a number associated with the magic labeling that is called magic constant or magic index. It is the smallest value wherein which, of course, any magic value we get magic constant. But if you take it as an index of that particular graph, what is the smallest index, smallest number such a way that it is going to get this magic labeling. So K33, what we have shown is obtained from our magic labeling of magic squares. It is 15. Any guess what is the reason why it is the smallest value? Because we are getting all the distinct numbers there. It's an injective labeling as well as every edge is getting distinct values. This comes into another category of magic labeling. It's in fact. However, this is found out to be this. There is no choice other than this because we don't get any other numbers. 1 to 9, every vertex is, every edge is used. Every edge is having the labels. Therefore, this is smallest one. Now, can you just show that the magic constant of K55 is 65? From the diagram with the magic square, it is immediate. A moment, please. Can you find out the value of this magic constant or magic index of K2m plus 1, 2m plus 1? Can someone find it out? It's quick. K33 is 15. It's a sequence you can develop. K55 is 65. K2m plus 1. K2m plus 1. Using this 2m plus 1, can you find a formula for that? Magic constant. It is not difficult to get this formula. What is the constant of magic constant of K2m, complete bipartite graph with the partite sets with the vertices 2m plus 1 and 2m plus 1 and denoting the odd numbers. What is the magic constant of K2m comma 2m? Is the screen visible to you? There is a message here that screen is not visible.
Screen is visible, sir. Screen is fine.
Audio is also right.
Audio is also fine. Very clear.
Thank you so much. So some are sending the message. Sorry.
No, maybe they have the network issues.
Okay. So evening you can do this exercise to this evening itself. What is the magic constant of a complete bipartite graph wherein which the partite set as having even number of vertices K2m comma 2m? Peterson graph, it is found out already, is 26. Complete graph where n is greater than 5, the value is found out when n is not congruent to 0 mod 4, n minus 2, n minus 1 into n plus 1 divided by 4. That is a formula for complete graph. Here comes an open problem. This is not an open problem, what I have shown earlier. It's easy to calculate. However, this is an open problem. Find the smallest magic index of a magic graph. It's a general open problem. There is no fixed value for this. Nobody has found out. So this gives you ample of scope for doing some simple but interesting research. Finding the magic graph, magic constant, a magic index, especially smallest magic index of a family of magic graphs, or generally it's an open problem. Now, it's an obvious question. Sorry, the previous that okay? Yes, thank you. Characterize graphs with magic index lambda. Okay, lambda is equal to 1. Do you have a magic graph? Lambda is equal to 1. Do we have a magic graph? Yes. K2. Lambda is equal to 2. Yes. Lambda is equal to 3. Yes. Give any value, you get it. So it is not a big issue. Then what is a big issue here? Exclude K2. It's an inverse problem. Given an integer, can you find a magic graph? It's an inverse problem in labeling. Given a number, can you find a magic graph with that as index? It's an unsolved problem. You can try that. What are the positive integers that are giving? A family can be obtained from K33, K44, from among all the families what you already found out. However, what are the forbidden numbers, integers that are not going to be magic constants, especially the smallest value? Once when you have the smallest value, we can find the remaining ones. It's an open problem. A slight variation of this, if we insist on this edge labeling is the prime numbers, we get prime magic labeling. Variation is you remove the injection to the natural numbers to the set of prime numbers. The smallest magic constant for prime magic labeling for K33 is, for normal magic labeling, it was 15. Now, when it comes to prime magic labeling, it comes as 53. We cannot use the earlier magic square logic for this. Of course, magic square helps us, but the early logic of creating magic square is not going to work here. And there is an issue with magic index is the smallest value that comes as the edge identifier, the constant, magic constant. The smallest magic constant for prime magic labeling of K44 is 114. K33 is 54. K44 is 114. No other graph it is found out. No other graphs prime magic labeling is found out so far. Just 2 bipartite graphs, complete bipartite graphs. Find the smallest magic constant of prime magic labeling of K55. A conjecture worth exploring. Every regular magic graph is prime magic. Every regular magic graph is prime magic. We go with the insistence of continuous labeling of the edges. If in case the edge labels are consecutive integers, that is from some number, you continuously +1 you add, and just consecutive integers. Generally, people work on 1 to number of edges, 1 to q, the number of edges, if it is a PQ graph. If the edge labels are consecutive integers, and if f star is a constant function, then we call it the super magic label. We already seen that super magic labeling. In fact, indirectly, we had seen for K33. This is a super magic labeling. All the numbers are used here, 1 to n. This is a super magic labeling. And later, any k 2m plus 1, 2m plus 1 also is going to give us, with this logic which I have shown you, it's going to give us super magic labeling. But astonishing thing is, although magic graphs are characterized, no characterization for super magic labeling has happened. Super magic graphs have happened. In line with, many are working on it, in line with the super magic labeling, magic graph characterization, people are working on it and different ideas are worked out. It's going to be a tremendous result if people can work on at least a partial characterization. But there are many independent necessary conditions. There are independent sufficient conditions. What is more interesting is, many cases people are working on regular graphs. It's easy to work on regular graphs. And so many results are associated with regular graphs. So please, in case we can work on non-regular graphs, can start with biregular graphs or tri-regular graphs and working on. How to start with this? There are, along with the magic squares, there are something called magic rectangles. Magic rectangles are close to biregular graphs. It would get KMN, biregular graphs. Magic rectangles. Kn is a non-result. Kn is super magic for n greater than or equal to 5. If and only if n is greater than 5 and n is not congruent to 0 mod 4. It's not a multiple of 4. We have this famous conjecture that G be an R regular bipartite graph of order 2n. If R is greater than n by 2, then G is super magic, except in the case n is an even number or R is not an odd number. R is an odd. G be an R regular bipartite graph. This R is important. If R is greater than n by 2, then G is super magic except for the two cases. N is congruent to 0 mod 2, n as an even number. R is an odd number. R is congruent to 1 mod. You might have seen this one, Mobius ladder. In fact, it's interesting it's easy to read, easy to draw this Mobius ladder in a different manner. I take this. You draw a cycle with one intersection. Yes. Then you add vertices. Oh, sorry. Okay. You go with that. It's not working very well here. So Mobius ladder, it's a ladder. It's a circular ladder in which just two edges are swapped. This is very important. Actually, among all the different graphs, this is very important as far as the super magic labeling are concerned. Mobius ladder, I just want to put it, M2n. N are super magic when n is greater than or equal to 3 and n is odd. N stands for the number of vertices in a cycle. It's actually one cycle only, but it's just half of the vertices. It's always a Mobius ladder will always have an even number of vertices, just half it, that is the n value, because the remaining problems are associated. Decide whether Mobius ladder, this is a challenging problem. Mobius ladder 2m plus 1 is super magic for some m. we can write a very strong paper on this. Decide whether Mobius ladder 2m plus m 2m plus 1. 2m plus 1 stands for one cycle you create out of 2m plus 1, one more cycle, then you connect them with the edges, make a circular ladder, remove 2 edges, that is joining these cycles, and swap them. This is an example for Mobius ladder. You can see, this is a Cartesian product, not Mobius ladder, Cartesian product. Very, very, very strong open problem is available in this area. All of us are familiar with the Cartesian products. Okay, I'm just Mobius ladder. I just show you how to. One easy, it's a circle and graph actually. One way of drawing is, I'm just finding the thing here to draw. Oh, come on. Yes, draw. Hope this will work. One way of, the easiest way is this one. The circular ladder is this. Then what I've told you, this deleting might be difficult for me. That was trouble. Okay, what you need to do is
You draw a circular path.
Okay, remove this and then connect these two.
Yes.
Remove this green in between. That alone I'm finding okay, it would go completely. No, another way of drawing that is the thing which I was showing you. Undo it. Yes, delete. What is that? Draw. Yes. Okay, that's done. So what you need to do is you just now draw the steps of the ladder here. This you might be remembering topology Mobius strips. This is the Mobius ladder. Whichever order we can. That's the easiest way of just one line itself. Okay, is it clear? Thank you. Oh my goodness. It is proved that Cn, okay, this was, I was speaking about the Cartesian product. It is a Cartesian product of C3 and C3. You can see this 3 C3s available in 3 different colors, then the joining edges. So go for any Cartesian product of cycles of the same order. It's already proved that Cn cross Cn is super magic, as well as C2m cross C2n. When both the cycles have even number of it. But strangely, Cm for any general graph, when m is even and n is odd and both ways. When both are of different parity, this is not approved. So one probably from taking the cue from the previous problems, we can try this. Finally, I come with the anti-magic labeling. Just the opposite of what we were looking at. We were getting constant value f star for the injective function f. Oh, it's edge set actually, not edge vertex. Vertex set, edge set is given injective labeling for the natural numbers. If f induces a labeling f star with some of the edges incident to a vertex, and if f star is an injective function, that is all the vertices are having distinct label, no more constant, then it is called an anti-magic labeling of the vertices. Anti-magic labeling of the vertices. Recently, in fact, I am reminded of one thing. If you want to read a very good article that has come recently, is just stop share. This has come in our journal, Indian Journal of Discrete Mathematics. Strongly anti-magic labeling is double spiders. It's a beautiful lab with a good conjecture available there. In case it's freely downloadable, Indian Journal of Discrete Mathematics, our ADMA journal. Every 6 months we are bringing out the journal, coming with the wonderful articles. This is one of the recent issue of 2020. This is carrying this excellent article known as the strongly anti-magic labelings of double graphs. You can download it from our website, ijdm.adma.co.in. Yeah. Non-results already associated with the anti-magic labeling are all the paths are anti-magic, cycles are anti-magic, complete graphs are anti-magic. Not all bipartite graphs, complete bipartite, only K2N are found to be anti-magic so far. And wheels are anti-magic. Among everyone who works on anti-magic labeling will encounter this particular conjecture, 1990 conjecture by Hartsfield and Ringel. 1990 conjecture, every connected graph other than K2 is anti-magic. Open remains, but as a reduced one is available, every tree other than K2 is anti-magic. This is available in this book, Pearls in Graph Theory, a comprehensive introduction by Hartsfield and Ringel. Now, every tree other than K2 is anti-magic. Already we have seen paths are anti-magic. So that is settled. Are there any other trees that are anti-magic? Yes. You can look at complete emery tree. That is anti-magic. Complete emery tree. Spiders are anti-magic. Spiders, you take a collection of paths, bring all, connect all, or just join all with a single vertex. Or it's a tree with exactly one of the vertices having degree 3. That way also you can present it. It's a tree with exactly one of the vertices is having 3 degrees. That's known as a spider. Just draw trees. Okay. Connect with a single, fuse everything with a single vertex, a spider web like thing. Anyway, they are not connected. So that becomes our spiders. Interestingly, not just spider alone, double spider also. 2 spiders joined. That also is found to be anti-magic. And some more graphs are there, trees are there, which are anti-magic. We just started working on some of these trees that are found to be anti-magic. The work is in progress. This is one challenging problem for each one of you to work on. but it's very, very thought-provoking one. Consider our bipartite graph KNN. Let sigma n be the smallest magic constant such that there is a prime magic labeling of KNN with n squared distinct prime numbers, such that n into sigma n is the sum of those n squared prime numbers. It's connected in many ways. KNN is a random KNN. We find out n squared distinct prime numbers because we require that many. For constructing the graph, you require n squared. You see that KNN graph prepared from magic square. So you require n squared numbers. We go for n squared distinct prime numbers. Sum them. If we can write it as n into sigma n, where sigma n is the smallest such value available. Therefore, we have to take the smallest set of prime numbers. Interestingly, looking a little weird, for n greater than or equal to 5, KNN has prime magic labeling with the magic constant sigma n. Do not get shocked. It's already proved for n between 5 and 17. And nothing else is done so far. Or already nothing else is known to us so far. So where do you get this information from? I just bring to you the major works associated with this collection of all. Hundreds of thousands of articles are available directly or indirectly dealing with all these magic graphs or its variations. But these are 8 monographs, books that would help you to have a very strong idea of magic graphs, anti-magic, as well as super magic graphs. The Wallis book came in 2001 with the name Magic Graphs. Bacha and Miller, Super Edge Magic Graphs. There are very varieties of actually vertex magic labeling is there, Super Edge Magic, Anti-Magic labeling, Edge Magic, EMD, VMD, so many different varieties are there. Then we have, I'm just winding up. This is again by this new edition, Magic Graphs by Mara and Wallis together. Vertex labels of symbol graphs. Fifth one is, okay, sixth. How to label a graph is good for generally a couple of labelings and harmonious labelings and other things, or new labelings. And this is the latest work in that area. As a monograph, as a book, it has come, available with the Springer. Magic and anti-magic labelings, attributes, observations, and challenges in graph labeling, dedicated to Mirka Miller. And finally, the recent dynamic survey. It gives you a volume of all the works that are associated with magic, anti-magic, and all the varieties of that. Gallian survey, dynamic survey. Thank you.
Thank you, Professor Varghese. I think we have lost the connection with Professor Muthuswamy. So let us take some questions from the participants. Yes, sir?
Yes, please.
Okay. So if anyone wants to ask any question, they can raise their hand. So first we have.
I shall leave the presentation in case if you want, you can distribute to them.
Yes, sir. You can mail me the presentation.
Yeah, yesterday's and today's. Or as a single one, I can send.
So Aruna Shakti, you can ask your question.
Yeah, good afternoon, sir.
Thank you.
Good afternoon. Sir, I have a doubt, sir. In magic labeling, anti-magic labeling, is it necessary that we should first label the edge?
That is a strategy we need to have. It's actually top down as bottom up. Both plans are there. It's actually you find a method of it's that I was mentioning in the beginning. It's a creativity. What do you have? There is nothing as such. You need to start with the edges, but you should have a guess. What would be if you are having, let's say, 30 edges? You have a guess of what is going to be the sum of that. It would never be less than, because we have to address to the edge labeled 30. 30 has to be added somewhere, and pendant edge is not available there. We cannot have. Therefore, one more edge has to come. So 30 plus 1 is the minimum one. Now look at that. We have to optimize. That is optimization we need to have. It would be a number lying between, the magic constant is going to be a number lying between 9 and we can have bound for each one. Not 9, I'm sorry. That largest value n plus a little more. So keeping that in mind, you need to work on. So there is nothing as such. Edge is going to be the starting point. We can have that by trial and error method, but we can have a list of, that is what initially I was mentioning about sense of integer partition, different partitioning of that. Thank you.
The other one question is, while we are defining the f star of uv equal to f of uv.
F. Yeah, F
is
of
it
uv.
necessary that operation should be multiplication alone?
It is not a multiplication. Actually, uv stands for edge. Every edge incident with the vertex v, that is standing for v, uv.
Okay, sir. That is f star of uv is equal to f of f uv.
Summation f of uv.
Oh, okay.
I show you once again. Yeah, it is here. This one. See, f star of v is equal to summation f of uv. Uv is not the multiplication. It is standing for all the edges incident with the vertex v.
Okay. Thank you, sir.
So next, Prem Prakash Mishra can ask his question.
Vijay Kumar sir is available there.
Yes, sir.
Ready. Yeah. Prem, please.
Okay, I think we have lost the connection with Prem Prakash. So Indrani, you can ask your question.
Excuse me, sir. Can you just tell me about the
About?
Hello. Can you tell me about that M array tree, sir?
M array tree.
Audible, sir? Yes, sir. Yes,
M array is, it's, you heard a binary tree?
Yes, sir.
You just a binary tree, what is about every vertex other than the leaf vertex is having?
Degree 2.
Degree 2.
Yeah.
And the root vertex also. Now
Yeah.
we give all the non-leaf as well as non-root vertex with m degree. M leaves for every m children for every vertex. Okay, your root also has. Yeah, m from m complete M array tree. We have a root vertex of m children, and each of the children would be having m children. Like that it goes, except the leaf vertices.
Okay, okay.
Complete M array tree.
Okay. Okay, okay. It's and one more thing, sir. The spider graph and star graph.
Spider graph.
And star graph are both same?
No, a star is having a spider reduced to actually just a path of length P2 alone. You take any number of paths, then join all of them with just connect all of them with a single vertex. That becomes spider. You remove all the edges, all the remaining. Or you instead of paths, you take a P2 alone. That becomes star. Or what you say is take a star, is subdivide at the edges. You get a spider. Oh, that's another way of construction. Take a star, subdivide. The subdivide means you just give a vertex each in between.
Yes, sir.
Yeah, you'll get a spider.
Yeah. Okay, sir. Thank you.
So we were drawing in that way. That might have caused the trouble. It was not. Actually, paths should have been taken. I was not getting the construction. Using this instrument here.
Okay, sir. Okay. I'll check, sir. Thank you, sir.
So next we have Kunal. You can ask your question, Kunal.
Hello, sir. Am I audible?
Yes, sir.
Okay. Sir, you told about in case of magic labeling, we have set of conditions with us. So how much is it possible for us to take help of computer programming to find out?
Many of us work actually, not us. I am not working as of now, but a little programming. But generally, many people are using extensive programming techniques for labeling. Especially Python is a very useful technique for that. And it is useful in many of the issues associated with its application. So computer is going to help you a lot in labeling.
Okay, sir. Is there any book?
With only yes, sir. How to label a graph is very interesting one by Chartrand. How to label a graph. It's not all the labeling, but all the reason labelings are used in it. How to label a graph. I was showing it here. Read actually dynamics. This is freely available. Actually, the last work, J. Gallian, Dynamic Survey of Graph Labeling. You can download it. It's free. It's available. It's freely available. It's the latest work actually. Okay. It gives you every labeling around. Oh my goodness. You would.
So I was asking for a programming book.
Programming
for labeling.
Actually, you can take graph classes. It gives you the complexity and not programming as such, but the algorithms. Not graph classes. Website is just search for graph classes.
Okay. Is the same package for Python? Graph class? Is it a name of package?
I'm not using it actually. You can create your own. There is a graph package, and it definitely patches would be available.
Okay. Thank you, sir.
Sir, so one more question. It is from Vijay Lakshmi. So Vijay Lakshmi, you can ask a question.
Good evening, sir. I'm Vijay Lakshmi from Chennai. I am pursuing research in graph labeling, sir. Hello.
Yes, ma'am.
Yes, ma'am. You are audible.
My question is on generalized graph. What are generalized graph and how we can frame it with any binary operation? And for example, if any graph G with binary operation, any binary operation, and G, if G star G, then is this generalized graph? Or G star any particular graph like cycle or star, G star cycle, G star star, G star fan, are these generalized graph? Are they both same? If we prove for one such graph like G star G, is it applicable to all the other graphs also?
Not in general. Not in general. There are some operations, binary operations, that give you all the other graphs getting a hereditary property that is being transcended, or I call it a transferred property getting transferred to the other one when you make a product with any other graph. Many different operations will not be getting the property of the subgraph to the supergraph that is being created. That's not a general result, but there are properties wherein which we can identify which is going to be, just because of the influence of a smaller graph that is available there, it is going to have the larger graph. For example, you take a tree and then you take in the case of okay, again that is not a general graph again. So, but the example that was in my mind. What I was saying is a click operation with any of those. So you will continue to have the click available there.
Okay.
Click and a tree. Yeah, I'm not getting some simple example, but that is not a general load. It's an interesting area wherein which you can think about an operation, binary operation, wherein which a general graph G operated with another graph, taking all that newly formed graph, the product graph is taking many of the properties of this second graph, G star H. The properties of H is being transferred to G star H. It's interesting to note at least some of the properties.
G star H, yes, sir.
General graph is any random graph. Some are asking what is general graph. It is any random graph, right?
Random graph which satisfies a particular labeling, right, sir?
Oh, okay. I thought just any random graph.
can we take any random graph, or to prove the operation to generalized graph to be to satisfy particular labeling, or should we take first G as a graph which satisfies a particular labeling, and we have to prove G star H is satisfies the particular labeling? Should it be like this? Should we assume G to be satisfying the particular labeling, or can it be any graph?
A particular property or labeling, yeah.
Okay.
It's interesting work, but I'm not sure. I'm not getting the idea of the enlightenment on that. But it's an interesting observation.
What happens if the operation doesn't fall under that such particular labeling, sir? Can we prove it for non-admit also?
You create a new operation. Any amount of products available defined. You create a new product which is satisfying this condition. That's the best way to attack it. There is this book by Closer, product of graphs.
Okay, sir.
So you can use that as a clue. At least 19 different graph products are mentioned in there. But you can think about constructing new graphs with this binary operation, which you define it as binary operation, and then go ahead with that.
Okay, sir. Should it satisfy? Should it admit that such labeling, or need not admit?
Yeah, both ways. Both ways you can attack.
Yes. Okay.
Then one is target, either it would always have the property that is transferred. One will never have that.
Okay. Okay. Thank you, sir. Thank you, sir.
Okay, sir. So that
operation you must be remembering. My cell skin operation you must be remembering. That's an operation that is created to increase the chromatic number. So similar way. So after the operation, you will not get all the chromatic number. It's always +1. Okay.
So may I know the book, sir, which you said now? May I know the name of the book for product for operations?
Sandy Clauser's product graph.
Okay, sir.
An
Thank you, sir.
extensive work on product graphs.
Okay, sir. Thank you, sir.
Okay, thank you. So that was the last question that we will take. Others can mail Professor Verghese if they have any doubts. Okay, thank you, Professor Verghese, for such a nice lecture on magic, super magic, and anti-magic labelings. Thank you, sir. So next lecture is by Professor Vijayambat Kumar. So he will be talking on power domination problem. He's a emeritus professor in Department of Mathematics, Cochin University of Science and Technology. He has done his PhD from Cochin University of Science and Technology, and then he has large number of invited talks, good number of research papers to his credit. So we invite Professor Vijayambat Kumar for his lecture. Please, sir.
Thank you.
Yes.
And very good. Am I audible and visible?
Yes, sir. You are audible and visible also.
Yes.
Okay. So this is around 3:15.
Yes, sir.
So it is usually a tea time for the usual conference.
Yes, sir.
We don't have an usual conference. It is online. So we will proceed with the talk. I will. Is it okay now?
What, sir?
Are you clear? Seeing my slide?
No, sir.
No.
Yes, it's coming, sir.
Yeah, now it is there.
Okay. Is it okay now?
Yes, sir. It is fine.
Fine. Thank you. I'm from Cochin University, and I will be talking on a theme called generalization of domination. There are several variations of dominations, like connected domination, photographic domination, independent domination, and so on. So I will discuss a generalization of the notion of domination, which is due to Hennings and others around 2002. So before I start, I dedicate this talk to Laszlo Lovaas, who received Nobel Prize 2 days ago for the year 2021, sharing his Nobel Prize with Avi Wittgerson. And all of us graph theorists should hear his acceptance lecture, which is available online, the YouTube also. The need for combinatorics people and graph theory people coming together to showcase the applications of graph theory in various fields. So that's a very important point that we should, especially youngsters, should take care of when they are talking about graphs and networks and so on. So this is our research group, which turns 30 years. So today, of course, all of them have become teachers, some of them university teachers, and they are all employed. Today, I'll be focusing on the works of Seema Varghese and Seetu Varghese. They are sisters. Both of them studied at Cochin University of Science and Technology for masters, and later on, both of them completed PhD with me. So the work on power domination that I'm going to discuss is mainly on by these two sisters. So this group is 14 number, and that is we are going to close it because I've already retired. So UGC doesn't allow me to guide more students. So this is the situation. Okay. So I have a long agenda, maybe 9 points, but I will cover only three or four today and leave it for tomorrow. So basically, the domination problem was motivated by the problem on chessboard to find the minimum number of queens that could be placed on a standard 8x8 chessboard in such a way that each square that was not occupied by one of these queens was attacked by at least one queen. So this is the famous puzzle, well-known puzzle of queens problem. And the minimum number of queens that can be placed satisfying this condition turns out to be 5. So queen's domination number is 5 for 8x8 chessboard. What is interesting is there are more than 4,800 solutions for this. And one of the solutions is this. If you place these 5 queens along the red dots, red squares of the chessboard, for example, first row, first column, third row, third column, fifth row, fifth column, and so on. If you place 5 queens there, it is either the queen occupies the square or it is attacked. Each square is attacked by the queen. So it satisfies all the conditions. Therefore, 5 is enough. 5 is minimum that I should have. So this is the well-known queen's domination problem, which is supposed to be a puzzle that gave birth to domination problems. And formally, if you want to define what is a dominating set, a subset of vertices is a dominating set. If each vertex of these that is not in S is adjacent to at least one vertex of S, and a dominating set of minimum cardinality is what's called the domination number, denoted by gamma. Throughout this lecture, we use this notation NGV, set of all neighbors of V, set of all vertices which are adjacent to V, and the NG closed bracket V is NGV union V, the closed neighborhood, including the point V. And if you take any S contained in VG, subset of VG, you look at all possible neighbors of V, closed neighbors of V, that forms the neighborhood of S. So if we take this example, it's well known, it's very simple to conclude that I need 3 vertices to take care of the definition of a dominating set. Every other vertex is either should be adjacent to one of these vertices. So UVW is the minimum, and therefore the domination number of the graph is 3. Now, there is a notion of bondage number, which is actually a parameter to measure the vulnerability of the interconnection network under failure. That is, I'm interested in finding the minimum number of edges whose removal makes the domination number greater than that of the graph. So minimum of that number of edges is what's called the bondage number, an idea due to Fink as early as 1990. So formally, the bondage number of a non-empty graph G is the minimum cardinality among all sets of the edges of G, such that gamma G minus B exceeds gamma of G. So that is the famous bondage number. And if you want an example, this is a graph with gamma G is equal to 2, which is domination number is 2. Its bondage number is also 2 because if you delete this edge and this edge, then you can see that the domination number increases. Therefore, and 2 is the minimum number of edges. Therefore, the bondage number is 2. So exact values of this bondage number for some classes of graphs and the very sharp upper bounds are found in the works of Hartnell in 1994 in a paper which appeared in the Discrete Mathematics. And there is a 60-page survey by Xu on the bondage numbers of graph, which appeared in International Journal of Commutations. That's a good survey, those who are interested in bondage numbers. We can easily calculate the bondage number of some special classes of graphs called complete graphs, paths, and cycles. We have a bondage number of Kn is ceiling n by 2, and then bondage number of Pn is 2 or 3 according as n is 1 mod 3 or otherwise, and bondage number of Cn is 3 when n or 2 according as n is equal to 1 mod 3 or otherwise. So these are all basic results given by Fink as early as 1990. And for a tree, non-trivial tree, we can prove by a result of Xu that bondage number is less than or equal to t or 2. And in fact, we can characterize those trees for which BT is equal to 1 or 2. It's a slightly involved thing, so I'm not discussing this here. And we have a theorem that if G is a non-empty graph with unique minimum dominating set, then the bondage number is equal to 1. And of course, the converse is not true. And if any vertex of a graph G is adjacent to 2 or more vertices of degree 1, then also we can see that the bondage number is 1. There is also a theorem by Hartnell and Douglas Rourke, which says that if G is a connected graph, we're going to get the bounds in terms of the maximum degree and the edge connectivity. So the bondage number cannot exceed the sum of the edge connectivity maximum degree minus 1 for any connected graph G. And there is a family of graphs which satisfies the tight bound. The bound is sharp. So if you take C 3k plus 1, starting from k is equal to 1, so starting from C4, C7, etc. For any cycle, it's which is a multiple of 3, it is 3. So bondage number of C3k plus 1 is 3. And connectivity of C3k plus 1 is 2, and lambda is also 2. It's a 2 connected graph, both vertex connected and edge connected, and maximum degree is 3. Therefore, if you look at lambda of G plus delta of G minus 1 for G is equal to C3k plus 1, what you get is 3, which is the bondage number of C3k plus 1. Okay, but because of the fact that kappa G is less than or equal to lambda G is less than or equal to delta G, the famous Whitney's theorem that the Whitney's inequality between the vertex connectivity, edge connectivity, and maximum degree, which says that kappa G is less than or equal to lambda of G and is less than or equal to delta of G. And in fact, there is a nice construction for any A, B, C, such that A less than or equal to B less than or equal to C. We can construct a graph G with the kappa G is equal to A, lambda G is equal to B and delta G is equal to C. So motivated by the above theorem and wideness inequality, Dunbar and Haynes in 1998 gave a conjecture that BG domination bondage number is less than or equal to vertex connectivity plus delta G minus 1. Delta G is the maximum. But that conjecture turned out to be false. And in 2003, 5 years after the conjecture was proved, Liu and Sun disproved this conjecture. As a counterexample, we have you take H, this graph, and if you take two disjoint union of H and fuse it with the vertex of degree 2, that is identifying two vertices of degree 2, then you keep two disjoint copies of this H and identify two vertices of degree 2. We call this as G. For G, we can prove that its bondage number is at least 5, greater than or equal to 5. And it's a G is a, it's a 4 regular graph with a maximum degree 4, and kappa G is equal to 1. And if you remove these two edges, if you remove this vertex, you get this connection. And similarly, if these edges, you get disconnection. So kappa G is equal to 1 and lambda G is equal to 2. So you don't get the equality there. In fact, bondage number 5 is greater than delta G plus kappa G minus 1. So this simple counterexample disproved the conjecture of Dunbar. And there is also some bounds for well-known bounds for the bondage number. BG is less than or equal to n minus 1, and BG is less than or equal to mass degree plus 1 if combination number is 2, and bondage number is less than or equal to n minus dom G plus 1. And all these three bounds are attained for the complete T-apartheid graph where T is equal to n by 2 and n is less than or equal to 4 and in integer. Okay. So with this information about the bondage number and the domination number, I will move to the main point of discussion of what is called the power domination problem. So I will spend a few seconds, few minutes to explain to you the motivation for this power domination problem. As I mentioned earlier, the motivation for the domination problem was puzzled in a chessboard. And this is something to do with electrical power networks. So basically monitoring of electrical power networks, that is the motivation for the power domination problem. A power network contains a set of nodes, what we call buses, and a set of edges connecting these nodes. So a power network also contains a set of generators which supply power and a set of loads where the power is directed. So in order to monitor a power network, we have to measure all state variables of the network by placing the measurement devices. A phase measurement unit, PMU, is a device placed on a node that has the ability to measure the voltage of the node and current phase of the edges connected to the node. And the PMUs are expensive, so I need to minimize the number of PMUs. So the goal for the power domination problem is to install minimum number of power phase measurement units such that the whole system gets monitored. So this was first considered in a paper in IEEE by Baldwin 1993, and it was modeled as a graph theory problem by Haynes, Kadernimi, and Henning in the Siam Journal of Mathematics, Discrete Mathematics in 2002. Of course, in any electrical power system modeling, the famous physics, two fundamental theorems of physics comes into help, what is called the Ohm's laws and Kirchhoff's law. So compromising on all such physics laws, the people have could reduce this problem to a problem of vertices. In fact, it was in 2005 by D.J. Brownie and Dorfling and Henning during 2005 and 2006, finally made this problem into a problem in related to vertices. So we are modeling this power domination problem of phase measurement unit, of minimizing the phase measurement units. And there is a famous statement, especially relevant in the case of the present pandemic. There is a quote by a famous statistician, Box, who says that all models are wrong, but some are useful. So that is the optimism with which all modeling people work. We cannot have a perfect mathematical model, and the mathematical model could be continuous mathematical modeling or discrete mathematical modeling, could be stationary, it could be dynamic, it could be stochastic. So many, it could be probabilistic. So many types of mathematical modeling techniques are there. But all of them, there is a general statement valid to all models, that all models are wrong, but some of them are useful. So with this dictum in mind, we are proceeding to model the problems of phase measurement unit using the notion of graph models, and that turns out to be a power domination problem. So what we have to define power domination is you are considering a graph G with vertex at V and edges at E, which represents an electrical power system where the vertex represents an electrical node and an edge represents a transmission line joining two electrical nodes. So two steps are involved, two rules are involved. One is domination step. A vertex with a PMU monitors its closed neighborhood. And propagation step, if a monitored vertex has a single neighbor which is not monitored, I'm going to use that also in the monitoring. It also gets monitored. So I will explain it more detail in the next slide. And the minimum number of PMUs that monitors the whole graph is what is called the power domination number, denoted by gamma PG. So let us formally define for a subset S contained in VG, the set monitored by S is recursively defined as follows. First step is what's called domination step. What do? I start with S and adjoin to S all neighbors of S. That means all neighbors of all the vertices of S. So that is my MS. And as long as there is only one neighbor of V, which is not already monitored, I'm going to suppose W is that the only neighbor which is not already in MS, but is also a neighbor of V. I'm going to add or adjoin this W also. So I'm going to enlarge my M of S to M of S union W. So what is W? W is the only vertex which is neighbor of V, which is not already included in my MS. That is the monitoring set. So just keep on doing this. And if you can fill the whole graph with this process, and if you take the S to be the minimum, then that is what's called the power dominating set. So as an example, if you take, if you take S is equal to just UV, this is not an example of a power domination set, but an example of MS. How do you find the subset of H monitored by S? So you start with U and V. So I will work here because the figure is symmetric, graph is symmetric in some sense. So I start with U. So I'm taking the first neighbors of U. So first neighbors of U up to reaches here. And if you take this vertex or this vertex, this is the only, if you take this vertex, sorry. If you take this vertex, which is already in my first level of N of S, there is only one vertex, which is not a neighbor of, which is a neighbor of U, but not already included. And similarly, so this comes here. When you have this, you can proceed to this because this is the only neighbor of this vertex, which is not at monitored. So I am including that vertex also. So that is how you get M of S. Okay, so we start with S is equal to U of UV. This is the M of S, and you know M of S is not the full graph. Therefore, this is not a dominating minimum dominating set of a power dominating set. So just an example of a set to show you what is a set monitored by a subset of vertices. So Formally, as I said before, by Haynes and others, Teresa Haynes, Adednimi, and Henning, that a set is called a power dominating set. If you keep on doing this M of S, that is the set monitored by S, is the entire graph G, and the cardinality of the minimum cardinality of a power dominating set of G is what's called the power domination number. So power domination is a generalization of the usual domination, because in the case of a domination set, we stop with the first step, that is what's called the dominating step. And in the case of a power dominating set, we are applying the propagation rules followed by Ohm's and Kirchhoff's laws also, and to get a power dominating set. So if you take the famous Peterson graph, the power dom number of Peterson graph is 2, because if you take U and V, these two vertices, if you follow the domination rule, it is the all saffron colored nodes are in the dominating step. And if you take this vertex, these two are already in my MS, and this is the only vertex which is a neighbor of this, which is not already included in the monitoring set. Therefore, as per the definition, I am going to include this vertex also. Similarly, this vertex also, and this is the blue vertex also. So all the saffron colored nodes are included in the dominating step, and all blue colored nodes are included in the propagation step, and they are filling all the vertices of the Peterson graph, which are 10 in numbers, have been taken care of. Therefore, by definition, S, which is UV, qualifies to be a minimum power dominating set, and therefore its cardinality is 2. Therefore, my power dom number of the Peterson graph is 2. And this is a very famous graph named after, in fact, I put the title. I just wanted to ask the audience whether they are familiar with this graph. And I don't expect a complete answer, because this is a purely Indian graph named after great commentatorialist and Euler's spoiler, which Professor Sethuraman mentioned yesterday, because Professor Srigande is the academic grandfather of Sethuraman. And this is the famous 16 vertices 6 regular graph, which is called a Srigande graph. You know, Srigande is popularly known as Euler spoiler by disproving a 170-year-old conjecture of Euler, along with his group R.C. Bose and programmer E.T. Parker. So R.C. Bose, Srigande, and Parker, 1958, they disproved the conjecture of an Euler on mutually orthogonal Latin squares. During the process of investigation of these mutually orthogonal Latin squares as well as association schemes, he came across a graph called Srigande graph. And Srigande graph is a graph with 16 vertices, 6 regular, which is an integral graph, in the sense that this is a graph which is 6 regular, therefore it is Eulerian. You can see that it is Hamiltonian, and you can see that its chromatic number is 4, and so on. So its power domination number is 2. These two blue vertices qualifies to be the power domination number, and that you can easily verify. Okay. So power domination number is a generalization of domination number. Therefore, for any graph G, one gamma Pg is less than or equal to gamma of G. And there are examples of graphs which satisfies gamma Pg is equal to gamma G. Not only example, you can construct for every K, you can construct a graph G such that power dom G is equal to dom G is equal to K. And that's not difficult. If you take a path of order K and take its corona with K2, Pk corona K2, that is, you have a path of length K, and each vertex of the path you take you adjoin with a copy of K2, so you get a triangle at each vertex of the graph. That is my Pk corona K2, and you can easily see that its power DOM number and DOM number are both is equal to K. Not only that, this gamma G minus gamma PG could be arbitrarily large. For that also we have examples like we take a star K1K and take its corona with K1. You get a graph whose power DOM number is 1, which turns out to be a spider. In fact, Professor Joseph also mentioned about spider in his earlier talk. I will define formally what is a spider. And this graph, that is K1K, corona K1, is a graph. It's a tree with whose power DOM number is 1 and domination number is K plus 1 for any K greater than or equal to 1. So what I said was, there are examples of graph for which gamma P G is equal to gamma G, and there are examples of graphs for which gamma G minus gamma PG is arbitrarily large. So if you take the family Kn, Cn, Pn, and K2n, complete bipartite graph K2n, we can easily see that its power domination number is 1. And we don't have a characterization of all graphs whose power domination number is 1. Okay, to proceed further, I need the definition of a spider, which was already told by earlier speaker, Professor Joseph. So spider is a tree, and you keep on subdividing the edges of the tree any number of times. What you get is a spider. So spider is the tree formed from a star by subdividing any number of its edges any number of times. So that's an essential idea due to Haynes. In that Bible, you know, there are 2-volume books on fundamentals of domination in graphs. It is well known, and that contains all these definitions. So if you take a tree T, among the class of all trees, we can characterize those trees whose power DOM is equal to 1. And that is the interesting theorem that for any tree T, power DOM number is 1, if and only if T is a spider. And further again, for results on trees, a vertex adjacent to a leaf is called a support vertex, and a vertex adjacent to 2 or more leaves is called a strong support vertex. For any tree T of order at least 3, again, gamma PT is equal to gamma T. The power DOM number of T coincides with the DOM number of T, if and only if T has a unique gamma T set S, and every vertex in S is a strong support vertex. You can try to get examples of trees for which power DOM number coincides with the domination number. And there's also an interesting observation about the power DOM number of a tree in terms of what is called the spider number. I will illustrate this. So the spider number SPT of a tree T is the minimum number of subsets of T into which a minimum number of subsets into which BT can be partitioned so that each subset induces a spider. So minimum number of subsets into which the vertex set of T can be partitioned so that each subset induces a spider is what's called the spider number of a tree. And we have a theorem again due to Haynes and others that for any tree T, power DOM number is equal to the spider number of the tree, where SPT denotes the spider number of the tree. Fine. So for any tree T, we can view the power domination set number in terms of its spider number. So I'm going to illustrate this as an example. To take this tree, you know, obviously on the left you have partitioned, or you have made into 3 groups the spiders. So as you see the maroon, these violet dots, red dots, and green dots. So this is the minimum number in which I can partition the vertex set of the tree T into 3 spiders. So the spider number is 3. And we can easily see that the power domination number of this tree is also 3. It's also 3 because if you take these blue vertices, we can see that this is the minimum power dominating set. As you see in the first level, what do? I get these also included in the dominating step, because all the neighbors of this vertex are included in the dominating step. So these are the only points, only vertices which come under the dominating step. Therefore, I have to use the propagation rule. What is the propagation rule? Whenever there exists a vertex which is already included in the MS, that is the monitoring set, and if there is only one neighbor of that which is not included in this set, which is still a neighbor of the set of elements in the monitoring set, which is not included, then I am going to include that also. So at the second level, this is what is happening. And at the third propagation level, this is the only vertex which is a neighbor of this, which is not already included in the monitoring set. Therefore, at the next level, I am going to include this also. I suppose the propagation steps are clear. So I will, I will start again. So dominating level, this one. First propagation level, this one. And at the second propagation level, we are getting all the vertices. So starting with these three vertices, bigger blue, I am going to get the whole vertex set of G. Therefore, by definition of power domination number, 3 is the minimum. I cannot do it with 3. So 3 is the power domination number, and 3 is also the spider number of this. So in the case of a tree, I shall repeat this result, because for any tree T, the power domination number of T coincides with the spider number of its spider number of that. Well, again, we will proceed with some basic results. If G is a connected graph of order at least 3, then there is again a bound for gamma power domination number of G. It cannot exceed n by 3, and the bound is sharp. And the bound is sharp if and only if G is K33 or G is the corona G dash corona H2, where G dash is any connected graph and H2 is either K2 or K2 complement. So K33 is well known, and it has got 6 vertices, and its power domination number is 6 by 3, 2. So that case is easily verifiable. So to understand the other condition, that is G is the corona of any connected graph with K2 or K2 complement. I have shown an example to take G dash to be K3, K3 corona K2 is this graph, and P4 corona K2 complement is this graph, and this has got 9 vertices, and you can easily see that the power domination number is 3, and this has got 12 vertices, so 12 by 3 is 4, and you can easily see that these 4 blue vertices are the power dominating, are the elements of the power minimum power dominating set, so that qualifies to be the power domination number. Again, some more results. If G is a connected claw-free graph, claw-free means there is no induced K13. So I want the graph to be cubic also. So if I have a graph which is of regularity 3, it's a 3 regular graph which is free from a K13 as an induced subgraph. We can prove that its power dom number cannot exceed n by 4, and with equality if and only if my G belongs to the class dk, where dk is the connected flow-free cubic graph formed from k disjoint copies of k4 minus e. So this is a k4 minus e, this is a k4 minus e, and this is also k4 minus e. So I've taken 3 copies of k4 minus e, and these 2 vertices of degree 2 are joined in pairs. So pairwise, so this is joined, and this is also joined. So this is my dk. So I shall repeat. What is a dk? I take k disjoint copies of k4 minus e. In this case, 3 disjoint copies of k4 minus 3. So it is d3 actually. And there are 3 pairs of vertices of degree 2 in this. So I'm joining by them by an edge. This is also by an edge. This is another vertex of degree 2. I'm going to join by this edge. Okay. So fine. And we have one or two more results. G is an outer planar graph with a diameter 2, or a connected outer planar graph with diameter 3. then its power domination number is 1. What do you mean by outer planar graph? Any graph which has got an embedding in which each vertex, every vertex of the graph is in the same phase, which we consider as an outer phase. You know, by stereographic projection, a graph is embeddable in the plane if and only if it is embeddable in a sphere. Therefore, any what is called any phase can be made an exterior phase by stereographic projection, and graph is outer planar if I can enclose all the vertices. If I can put all the vertices in the same phase, such a graph is called outer planar. And just like Kuratowski's theorem for planar graph, there is a forbidden subgraph characterization for outer planar graph. You know, K4 and K23 are the simplest graphs which are not outer planar. So any graph which contains a homeomorphic copy of K4 or K23 cannot be outer planar. So that is the structure of outer planar graph. And if you take a planar graph of diameter 2, then we can see that gamma PG is less than or equal to 2. Okay, I break for a second here because whatever I told regarding this bondage number is available in the survey, and whatever we discussed on power domination number is actually available in the works of Haynes and others. And it's already 4. I will take 5 minutes more and leave this for discussion for today, and I will complete my target tomorrow if it is possible. So this is purely our work. So we'll concentrate. I will stop. I will discuss this point again. So power domination, some classes of graphs. So the classes of graphs, if you take again a literature survey, if you take the class of all bipartite graphs, quadral graphs, etc., its problem is NP-hard. It has got a linear time algorithm for trees, interval graphs, and block graphs. You know, interval graphs is the intersection graph on the family of intervals of an ordered set, and block graph is the intersection graph on the family of blocks of graph. And there is a characterization of a block graph. A graph is block graph if and only for its blocks are complete. Okay, so you can easily view a block graph, which is a generalization of a tree. And there are results by Haynes, Xu, and others, which discusses the power domination number of these classes of graphs. This also closed formulas are available for some product graphs. This is not true in the case of domination number. And the honeycomb meshes, W pyramid works, these are all works of C2 Varghese, Seema Varghese, along with Andrea Sims and Daniela Ferrero during 2018 and so on. So this is a good piece of work by my own students. So we are going to look at the power domination number of 3 classes of meshes. And I will also conclude by sharing an excellent experience, exciting experience of what is the importance of these meshes. So I consider first the classical hexagonal grid, hexagonal honeycomb grid, which I will denote by bracket n, minus n plus 1, minus n plus 2, etc., minus 1, 0, 1, 2, 3, etc., n. So the hexagonal honeycomb grid of dimension n, excuse me, hexagonal honeycomb grid of dimension n greater than or equal to 1 consists of vertex sets, all x, y, z belonging to this group, 0, 1, 2, 3, etc., n, minus 1, minus 2, etc., up to minus n plus 1, whose coordinates x, y, z satisfy x plus y plus z is less than or equal to 2 and greater than or equal to 1. So these are the vertex sets of the hexagonal honeycomb grid. And 2 vertices x1, y1, z1 and x1, 2, y2, z2 are adjacent if and only if modulus x1 minus x2 plus y1 minus y2 plus modulus z1 minus z2 is equal to 1. Okay, so this I will show you as an example. So this is the hexagonal grid XM3, and so 3 tuples will be there, and this 0, 3, minus 2 and 1, 3, minus 2 are adjacent because if you find the difference mod x1 minus x2, mod y1 minus y2 and mod z minus 1 minus z2, it is equal to 1. So that is the defining relation of the adjacency. This is the defining relation for all coordinates. Sum of the all coordinates lies between 1 and 2. Sorry, each coordinate has x, y, z. X plus y plus z lies between 1 and 2. That's also true. 1 plus 3 minus 2 is 2. Okay. So this is the honeycomb mesh. And we'll take a triangular grid. What do I do for triangular grid? Triangular grid is Tn is the graph whose vertices are ordered triples ijk of non-negative integers summing to n. And two vertices are joined by an edge if they agree in one coordinate and differ by 1 in the other two. Okay, so as an example, this is the T5. So 0, 5, 0, the numbers are all vertices ijk summing to n. Okay, so summing to 5. So 0, 5, 0, 1, 4, 0, 0, 4, 1, etc. 1, 1, 3. These are the vertices of the triangular grid. And any two of them are adjacent. How is the adjacent? If the edge connecting two triples, if they agree in one coordinate and differ by 1 in the other two, so at least they have a common first coordinate, second coordinate, or third coordinate. So 0, 5, 0 and 1, 4, 0 are adjacent because 0, 1 coordinate is same. Okay. And the second condition is that they should differ by 1 in the other two exactly. So 4 and 5, 1 and 0. And the third coordinate is the only coordinate for which the coordinate is 6. So this is the triangular grid. And one more. What's called the rectangular triangular grid, which consists of all vertices ijk, whose I belong to minus n m, and j belongs to 0 m, and k belongs to 0 n, and such that mod I plus j plus k is equal to n, with an edge connecting two triples if they agree in one coordinate and differ by 1 in the other two. So you get this is the rectangular triangular grid RT5, 6. And for all these graph classes, we have a closed formula for the power dom number. If G is HMN, rectangular grid, it is gamma PG ceiling of 2n by 3. That's why n is equal to 3, you get 6 by 3, which is 2 in the earlier examples. And if it is Tn, that is triangular grid, its power dominant number is ceiling n plus 1 by 4. And if it's a rectangular triangular grid RTMN, its power dominance number is ceiling m plus 1 by 4. And this is, as I said, the works of Sima Varghese and Sima Varghese along with Daniela Ferrero. And this is interesting result. So these measures, I will stop in 1 second. These triangular grids, and for that matter, all these grids come as an application in the brain network. It seems that the human brain sends message through cells which are grids. So that's a very exciting application of using this, especially triangular grids. At the point of time when we discussed the domination number of triangular grids, we thought that why triangular grids? And when I refer to the, even if you refer to the Google and ask for triangular grids applications in brain networks, you will see this information that brain neurons communicate or pass signals through cells or cellular grids like triangular grids. Okay, so I think I have to stop here because though I started late, it's not proper to hold on people. So I will stop here at with this slide. So 2 slides I have covered. What's called the classical bondage number and power domination, basic power domination bounds, and power domination in the 3 classes of measures. And what remains to be done is that I will do tomorrow, especially on power domination on product graphs and generalize. We are going to generalize the power domination notion and heredity notions and bondage notions in the power domination set. So that's all for today. And thanks for this opportunity to come all the way to Delhi. Okay, I didn't travel at all. I'm sitting in my room. And some plus points of this pandemic is that we can still meet though we are not actually meeting. We are assembling for a common cause of spreading the various notions of graph theory and its applications to various areas. Okay, so thanks, Dr. Rajesh. If there are some questions to take, I'm ready to spend some time.
Okay, so participants, you can raise your hand for questions, and I will take questions one by one. So first we have Pavitra. Pavitra, you can.
Can I stop sharing?
Yes, sir. You can stop sharing, or you can leave it as it is also. It's fine, sir.
Okay, so you are seeing me, right?
Yes, sir. We can see you. So Pavitra, you can ask your question by unmuting yourself. Okay, I think Pavitra is not there. Then Madhavi, you can ask your question by unmuting yourself.
Good evening, sir.
You please introduce yourself so that I know where are you from.
Yes, sir. I am Dr. Madhavi from Yogi Vemana University, Kadapa. Maheshwari Madam student, Mahila University, Maheshwari Madam.
Okay, okay.
Padmavati Mahila Vishwavidyalaya, Maheshwari Madam student,
Fine,
sir.
fine.
I am.
Oh, fine, fine.
I am doing in domination theory, sir. I am unable to understand the difference between total domination and power domination here.
See, total domination takes care of only domination level.
Yes, sir. Yes, sir.
Okay, so here what I do is I am propagating. I am not able to fill the whole graph with just dominating step.
Okay.
After dominating step, I am going to use what is called propagation rule.
Propagation
rule. I am going to adjoin with the minimum dominating set S or minimum monitoring set S. Any vertex which is not already there, but that is the only vertex which is not already monitored, I am going to include that.
So, sir, because I am doing research in arithmetic graphs.
Okay.
Arithmetic Cayley graphs I am doing. So, can I apply this to my work, sir?
That I don't know, because finding the power domination number of arithmetic graphs, is it interesting? I don't know. It could
because
be.
all of them are connected graphs, sir. They are all connected graphs. Recently, when I did one zero divisor graph, when I took, I got components also. I got disconnected component. The graph became a disconnected component.
Okay, okay.
So, is it possible? Because when I saw one paper on block graphs, just now you are telling, sir, block. So, is it possible for me to apply? Can I try?
Sure. Do you know the domination numbers of those graphs which you are dealing?
Yes, sir. Because I have done domination for vertex as well as edge. I calculated.
Okay.
Even I did my graphs for bondage number also I calculated. Now I'm again calculating for some graphs bondage number and all. So I didn't extend beyond that. So that's why I'm asking whether I can.
Definitely. If it works for domination, it should definitely work for power domination also.
Yes, sir.
It may not be easy, but you can definitely make a trial.
So when can I approach you, sir? When I try, can I approach you, sir, for any help?
Sure. I will also talk about this monitoring step again tomorrow morning.
Yes, sir.
So that you understand clearly what it is. And of course, I am going to leave the slides to the organizers.
Thank you, sir.
You can. A lot of papers are there in references. I will put it tomorrow.
Yes,
all
sir.
my references. You can try to work.
Yes, sir. Thank you, sir.
Okay, thank you.
Thank you very much.
Dr. Rajesh, I want to ask one question.
So please introduce.
I am Dr. Purnima Gupta, Dr.
Hello.
Vijay Kumar. How are you?
Good afternoon. How are you?
I'm fine.
Okay.
You said that if G has a unique minimum dominating set, then the bondage number is 1.
Yeah.
Do we know something or have about the structure of graphs having unique minimum dominating set?
I know some examples of graphs which has unique minimum dominating set. But you wanted to tell all graphs for which there exists a unique minimum dominating set. That's what you want?
Yes.
I don't know. I asked the same question to myself last night, but I don't have an answer. Graphs which has a unique minimum dominating set.
Yes, sir. And even for trees, it will be interesting to look at those trees which have unique. For smaller diameters we can see, but as the diameter increases, then it's a very good question. So that's why I thought to talk about it. And second thing was that you said that the bondage number of any graph is less than or equal to n-1.
Oh.
So are such graphs for which this upper bound is attained?
Yes, sir, it is there. Actually, it is there in the survey paper by XU. I didn't take it down here. I can tell you tomorrow what is the graphs for which the bound is attained.
Yes, yes. Are such graphs characterized? That's my question. If they are not characterized, then that can be looked at. That's what I thought to
okay, just. Okay. I will tell you that tomorrow.
Yes. And regarding bondage number, what is the in general bondage number of a tree? Has it been found?
Pardon?
Bondage number of a tree, has it been found?
Bondage number is less than or equal to 2.
For a tree, always?
For a tree.
Okay, okay. So that is done.
Okay. And the cases where it is 2 and it is 1, it's a large class, yes. It's a big class, that's why I didn't write it there.
Okay, okay. Thank you so much. Okay. These were the few.
Okay, madam. Thank you. Bye.
Sir, good afternoon. I am Muthuswamy from Periyar University.
How
are you, sir?
Fine, fine.
Normally, you seem to be very young, but it is different now.
Yeah, yeah. After retirement, I allowed more white hairs.
No, no, don't say that. Don't say that. You're looking younger.
Due to some internet error, I could not connect you at the beginning.
No.
See, you have your lecture was on power domination.
Yeah.
Is there any reason for having such a name? Did this number has some power on it?
No, no, no. This number is used in the monitoring of electrical networks.
Okay, okay.
So we require what are called phase measurement units
to
monitor the efficiency of the network. So I wanted to minimize this. Obviously, PMUs are expensive, so I want to minimize. So this came as a consequence of applying to networks the famous laws of physics, Ohm's law and voltage law.
Okay.
And modeled by Haynes in 2002.
So,
yeah.
Any relationship with the existing other domination parameters for this one?
Gamma P is less than or equal to gamma.
Okay.
And for other types of domination, I have not seen any work because people were working more on the bounds for this power domination.
Yeah.
It's a power bondage, which I will discuss tomorrow.
Okay. Okay.
Generalized power domination also. I have not seen how do you relate. That means in that chain of inequalities where you can put gamma P, isn't it?
Okay. Okay.
Yeah, that I don't know actually.
Will you discuss these parameters in the on product graphs also in the next?
Yes, product graph tomorrow. Yeah, product graph tomorrow.
Okay. Okay. Thank you, sir. Thank you. Thank you so much.
Sir, next we have Arun Nanan, who will ask the question. Please unmute your mic and ask your question.
Hello, sir. Good evening, sir.
Good evening.
Sir, this is Arulanan from Hindustan University, Chennai.
Okay, please.
Sir, I have a doubt on the propagation step, sir.
Pardon?
I have a queries on propagation step. Sir, first we have to do the domination step.
Yes.
Again, after that, we have to do the propagation step.
Yes.
After completing the propagation step, I have some vertex which is not covered by the dominating set. So in this case, I have to do repeatedly the propagation step, or what I have to do, sir?
Yeah, if you want to catch a minimum power dominating set, by propagation step, if you can fill the whole graph, and that set of vertices will constitute a power dominating set.
Okay, sir.
That is the first example which I gave you. I can repeat it tomorrow also if you want, just remind me. just closed it. Otherwise, I would have done it today itself. First example which I gave was I took with the two vertices, and these two vertices in that graph could not cover the whole vertex set by dominating rule and propagation rule.
Yes, sir.
So I may have to take one more, 3. That I didn't show. In the case of Peterson graph, for example, if you take two vertices, by dominating step, I can cover some of the vertices. And again, by next stage, that is the first level propagation step,
yes, sir.
We will be able to catch all the vertices. So power domination number of Peterson graph is 2, whereas domination number of Peterson graph is 3.
Okay, sir.
Okay, I'm actually extending slowly, just like viral attacks. I'm slowly from minimum first level, our neighborhood. I think this is also what is coronavirus is doing. Okay. First level is our neighborhood.
Yes, sir.
Second level is again further second neighborhood with the condition that if there is at least one neighbor of that vertices which is not already included in the monitoring set, only one, then I am going to put that also.
Okay, sir.
And this notion is generalized to generalized power domination. I can have at most k neighbors which are not already included. I can attach one by one. That's what we are going to tell tomorrow.
Okay, sir. Okay, sir. Thank you, sir.
Yeah, I didn't understand. Where are you from?
From Chennai, sir. Hindustan University. Thank you, sir.
Okay.
So next is Shiva Garan from. So Shiva Garan, please unmute yourself and ask your question.
Thank you, sir. Sir, good afternoon, sir. I am P. Shivagaran, student of Professor P. Paul Raja, currently doing postdoctorate fellowship in Annamala University, sir. Can you hear me, sir?
Yeah, sure. Tell me.
Sir, actually, currently I'm read some paper on power domination theory, including your papers also. So my question is whether there is any paper related to circular graphs, line graphs, and total graphs of graphs, sir. Is there is any bounds are found out?
Sorry, I didn't hear. What is the relationship between?
Sir, not relationship, sir. Actually, I try to working on power domination.
Okay.
So I plan to work on circular graphs. And then line graphs, circular graphs, sir. Circular graphs.
Circular. Okay. Yeah.
And then line graphs, and then total graphs, sir.
Okay.
I try to find the literature. So far, I cannot able to find any results on this family. So, if there is any paper available, sir, up to your knowledge?
Yeah. I have to check it.
Yes, sir.
Also, a good question could be how are the power domination number of graph and its line graph related? I don't know.
Okay, sir.
Similarly, domination also I don't know about such work.
Yes, sir. For
lot of work is there for both domination and power domination on product structure.
Okay, sir.
Other operators I don't know.
Okay, sir. Thank you, sir.
And we are doing something on Michelskian. When you know power domination number of G.
Okay.
We are trying to find the power domination relation with Michelskian.
Generalizer Michelskian graph you already completed.
We have already
yes,
done.
Sir. Yes, sir.
But line graph and circular graph, you want to compute the power domination number of circular graph. Am I right?
Yes, sir. Yes, sir.
But do you have a domination number result?
No, sir. Actually, Professor Tamil Selvan sir already worked on domination number of circular graph. So far, not yet completely settled.
I see.
But my intention is to find a power domination number of at least 4 regular circular graph for any to circular distance. I try to find out, but still I am facing a lot of difficulties because it is quite difficult to find a power dominating set rather than dominating set, sir.
If you can, I think I will leave my mail ID. You can send me tomorrow. Just remind me. I will give you my mail ID.
Okay, sir.
And you can send me the precise problem of circle and graphs.
Okay, sir.
Okay.
Okay, sir.
Okay.
Thank you, sir. Thank you very much.
So next we have Indrani. Indrani, please unmute your mic and ask your question.
Yes, sir.
Yeah.
Hello, sir. I'm Indrani from doing my research in graph labeling. Recently, I've come across more information about the dominating set and some more examples I want to explore. Is there any book, a good book to begin with, sir?
On power domination.
First one is dominating set itself. I want a little bit of clarity, sir. Then I can think of
dominating set. There are 2-volume books by Haynes and others. Fundamentals of domination in graph.
Yes, sir.
Fundamentals of domination in graphs. Volume 1 and volume 2.
Author, sir?
First author is Haynes. Haynes.
Haynes, sir.
Kadetnimi et al.
Yeah.
Yeah, pardon?
Hedetnimi. Hedetnimi.
Hedetnimi, yeah.
Yeah. Just Google fundamentals of dominations in graph volume 1 and 2. You will get, I think it is downloadable.
Okay. I'll check it out, sir.
Okay.
Thanks, sir. Thanks a lot, sir.
Thank you.
Rachna Soni, please unmute your mic and ask a question.
Good afternoon, sir. I am Rachna Soni from Bennett University, Greater Noida. I am first year PhD student of spectral graph theory, and I'm working on algebraic connectivity actually. Sir, my question is there any way to connect domination theory and spectral graph theory, any bridge or idea that I can make some connection between two?
I'm not sure because the whole spectral graph theory is in a totally different direction.
True.
Actually, you are dealing with the regular graphs and its characteristic equation and such things. I'm not, I don't know. Seems to be not feasible because the domination notion and the spectrum, I'm not sure whether such things can be done. I don't know.
Okay, thank you, sir. It is a pleasure to listen your lecture.
Okay, so sir, I think all the questions are over. So Professor Muthuswamy, can you please take over? Okay, there is one more participant who wants to ask question. Chandramani. Yes, please go ahead, Chandramani. Unmute yourself and ask a question.
Hello, good afternoon, sir.
Hello. Yeah.
Good afternoon, sir. Myself Chandramani from Tamil Nadu, research scholar. Actually, I am working with power domination only. Currently, I am working with power domination of middle graph of some graph, like power domination of line graph of something.
Okay.
Is this is it correctly? Shall I proceed the same way?
I have not seen works on line graphs. That's what I told you earlier also.
Okay, sir.
I have not seen. What is the first thing that you mentioned?
Middle graph of.
Middle graph. Okay.
Yes,
okay.
sir.
I'm not aware.
Okay.
Usually, this power domination number is calculated for some networks like butterfly network. So many examples of networks are there.
Okay.
So because it's related to the power distribution system.
Okay, sir.
I don't know whether it could work for your cases.
Okay, sir. Okay, sir. Okay, sir. Thank you so much, sir.
Thank you, Chandramani. So Professor Muthuswamy, please take over.
Yeah, yes, sir. Okay, on behalf of the organizing committee, I thank the speaker, Professor Ambat Vijayakumar, for the nice lecture on the power domination number. And he has answered almost all the questions raised by all the audience as well as the experts who have connected in this meeting. And I think he will continue his lecture on tomorrow on the same topic on the product graphs. And very nice lecture for the youngsters, those who are working on the domination problems they have taken for the research at the present time. So very nice things, sir.
Thank you.
Sorry for the meeting. I could not connect at the beginning. I would have introduced you at the beginning itself, but I could not.
Okay. You can introduce me tomorrow.
Definitely. Our friendship for more than 25 years. While you have conducted the conference at the Cochin University of Technology, maybe in 93 or 92, so 91. We are all the research scholars at that time. We have presented papers under the guidance
I was about to tell that I forgot because the last day of the conference was when the murder of Rajiv Gandhi took place, May 21. 1991.
Yes.
And those people who came from Delhi and all that, they could not travel beyond Chennai because of the disturbance in all over India. May 21 was the last date of the
very
conference.
Nice conference at that time.
Yeah.
As at the time of the research scholar, and we have been taken to many places also. Sightseeing trip at the
hopefully
Cochin.
such conferences can be held maybe another 1 or 2 years.
Okay, thank you once again for the nice lecture, and we will continue it tomorrow also. Thank you, sir. Thank you so much.
You have done a good job. Rajesh did a good job.
Thank you, sir.
Thank you. Bye. Shall we leave?
Hello, Rajesh. Whether the meeting is over?
Yes, sir. Thank you, Professor Muthuswamy, for sharing this session. So now I am ending this session.